Hey everybody, let's get started today. Get to move on to something a little bit more exciting. Even though chemistry was kind of exciting, today we're going to talk about cells. And that's going to be a topic that we are going to cover in lab tonight. Lab tonight is probably one of the best labs. It's going to be action-packed. And it'll be busy, and I think it'll be fun, and time will fly by. So those are the kind of labs that I like the most. So tonight's a good one. So lab tonight deals with cells and histology and mitosis. Today in lecture, we're only talking about cells. So if you have lab on Thursday, you're going to have the benefit of hearing a little bit more about mitosis and histology on Thursday, then go into lab. So tonight, if you have lab, there'll be some new stuff that you'll be introduced to and then hear more about on Thursday. So we're kind of winding things down. We have a full week of lecture this week. Next week, we only have, I believe, one lecture, and then it's our first test. So start thinking about that. And next week, I'll give you some practice questions so that you can think about whether or not you're preparing enough. I'm teaching a lot in the summer, and I'm teaching a class right now for biology majors at Xavier. And I just graded the first test, and so many students did bad. And it's just because they're just not putting in enough time. So I hope that you understand that in order to make it, not just through Cincinnati State, because that'll take a good effort, but in order to make it, so that you can do well on the NCLEX test, which everybody takes in the nation, if you're a nursing major, you really have to put in a serious effort to learn the material, not just memorize it. So that means daily work, daily time studying, not time on the weekends, but a daily reminder, a daily review. So it's still way early in the game, so if you haven't done that, make sure that you start thinking about next week and saying, need to start tonight, maybe spending 45 minutes before you go to bed or before you eat or whatever your routine is. Also, just want to make sure that we're all on Pearson at this point. So I haven't checked, but usually Pearson sends me a list of people who are actively participating, and I can go on, and not that I'm like, snooping or anything, but I can go on and see like when the last time you logged on and things like that. So I'll probably do that this weekend. So if you are having problems with Pearson, please let me know in lab today or in lab on Thursday, and we can maybe figure that out. So those are points that should just be like free points. It's kind of like the curve, really. I mean, it's just free points. Yeah.
Not to sound like I'm slacking on it, but I did work into one that I actually worked ahead on, and I got a couple of things wrong. Did you say the whole thing is completion?
Yeah, and everything online is completion, so I'm not worried about anybody's score. Main reason why I'm not worried about score is because there are a lot of questions that deal about things that we're not talking about. You might see questions like, what? We don't talk about this. So I have no control over choosing questions. That's the biggest flaw with Pearson as an instructor. But for you guys, I think the majority of the questions will help, so I still think it's beneficial. So talk to me in lab this week. This is kind of my last kind of reminder. I'm going to assume that if I don't hear from you in lab this week, that you're good. And just talk to me if you're having problems. Okay, so today it's all about the cell. And we're going to talk about cell components. And when we think of cells, today in lab, maybe we do this in biology lab as well, we're going to look at a cheek cell, which kind of looks like this. And it has this circular thing, a dark spot in the middle. And when we think of cells, we're going to say that today we're going to be looking at three major components: the plasma membrane. We're going to look at the nucleus briefly, and the cytoplasm. which is the liquidy environment inside the cell. So over the next hour and 5 minutes, we're gonna probably spend, listen to this, an hour talking about the plasma membrane. Probably spend 5 minutes talking about the cytoplasm, and then we'll spend the rest of the time talking about the nucleus on Thursday. So that's the plan, okay? So let's get started with kind of some information about cells. The way we identify cells is by looking at or using different types of microscopes. And the microscopes that we have in lab in Cincinnati State, as I told you, are really, really nice. And they allow us to see shapes. They don't allow us to see things inside the cells other than the nucleus. So it's kind of hard for some students to believe that there's things like mitochondria and things like that. But what we can do with our scopes is appreciate the different cell shapes and sizes. You already know the pain of looking at two of the smallest things in the body, and that would be sperm, and that would be red blood cells. If you can find sperm and red blood cells, there's not going to be one thing for the entire session and next session that will be smaller than that. So you found the hardest things. The only thing smaller than sperm and red blood cells would be bacteria, which is not this class. So maybe it was mean, but it was kind of a great exercise for you to start out with the hardest thing, just for practice. And once you feel like you can do that, every other slide should be a piece of cake. I had about 8 students in office hours this afternoon, and a few who really struggled in lab. And I think most people left today feeling like, okay, I just need maybe one more practice session, and I'm gonna be perfect. So, good. Today we're going to appreciate sizes and the fact that some look very unusual, like look at these. These are cells from our brain or our spinal cord. Look at these over here, your favorite, right? Blood. One of the unusual things about blood is that it doesn't have a nucleus. So you can't say that every cell looks the same. That's impossible. You can't say every cell has the same structures. So you have to appreciate differences. And the word histology, which is something we're going to talk more about in lecture, is the whole process of looking at things underneath the microscope. So we're going to hopefully get an appreciation starting tonight in lab and on Thursday. So here is a scanning electron microscope, and what you can see here is some three-dimensional structures. Not only do you see the big dark blob, but you can see there's things within the blob, and you can see some other things floating around, so they really do exist. And then here's what it kind of looks like with our scopes. So our scopes show a dark thing, maybe some specks, but we really have no idea, what those things really are, because we just don't have the capability to zoom in. Okay, do you guys think it's warm in here?
Yes.
Yeah.
Really, really warm.
If we open the doors, will it?
Okay, I'm gonna call them tomorrow, because maybe we'll figure it out, because there's no way. This is like claustrophobia, no air. Don't think about it, or else it get kind of panicky. We're all breathing the same air. Yeah. All right. Here is a cell that looks kind of, I think, unusual in that the plasma membrane has these little finger-like projections. And that's true with some cells, but definitely not all. So again, you have to say that you appreciate that cells look different. So when we look at the major constituents of a cell, we can classify them as 3 major kind of parts: the plasma membrane, the inner part, the cytoplasm, sometimes referred as the cytosol, and the nucleus. So we're going to start with the plasma membrane. The plasma membrane. Okay, so let's draw the plasma membrane. So if I'm drawing it, you'll probably have to draw it on the test. And when we draw the plasma membrane, we're going to start out by drawing a bunch of circles. In fact, we're gonna draw 2 layers of these circles. And these circles represent one of the major ingredients of the plasma membrane. Okay, so we start out by drawing 2 layers of something. Let's talk a little bit about the function of the plasma membrane. I'm gonna put in kind of quotes, it's kind of like the skin of the cell, which means that it's the outward covering. It's a great protector. And right now, if I rub my forehead, I'm feeling sweat because it's leaking sweat. I'm trying to cool off in this hot room. So one of the things about the skin, like the plasma membrane, is that it is somewhat leaky. Now listen to this. Some things can enter, some things can leave, but not everything. Some things, not everything. So we say that the plasma membrane, like our skin, is, ready, selectively leaky. No, selectively permeable. Which means some things can leave, some things can enter, but not everything, some things. If I'd ask you on the test, this would be a good question. What are the 2 main ingredients of the plasma membrane? The answer would be fats and proteins. So when we look at this drawing over here, we're in the middle of drawing some fats. So what I want you to do with each one of these circles, these heads, is to draw 2 tails. Okay, so that's good. What we have just drawn is a 2-layer or a bilayer of a fat called phospholipids. And phospholipids are weird because they have these circular heads, look, that love water. They love water. So we say that the heads are hydrophilic. They love to be around water. And then they have these tails that are fearing water, hydrophobic. So what's the big deal? Why is this cool? Because if you think of the layer that surrounds a cell, on the outside of the cell is very liquidy. Sometimes we call it the ECF or the extracellular fluid. And on the inside of the cell, we already said it's like a liquid environment, the cytoplasm. We call that the intercellular fluid. You're going to see those abbreviations a lot, ECF and ICF, outside and inside. And they're both fluid, water. So we have to have circle heads that are exposed to both of these regions. Does everybody get that? Okay, so that's one major ingredient. Let's talk about the second major ingredient. We'll make them red. So here we have some things that are stuck on the outside, some things that are stuck on the inside. And occasionally we have things that go all the way through. And these things that we're drawing are proteins. So the ones on the outside, this makes sense, we call these peripheral proteins. The ones in the middle we call integral means in the middle, proteins. And then the ones that go from the outside to the inside, we call these transmembrane proteins. And in your notes, put in parentheses that they can act as a channel. Sometimes people think of them as like a pore. So look, with this big protein, they can go in or they can go out. So I'm all about giving you as many questions as I can on the exam. You already know that there's going to be a table from last lecture, 1,000,000%. If anybody misses any of those, I know you're not interested in studying. I'm telling you that you have to draw the plasma membrane. So those are 2 short answer questions, and there's only like 8 of them. So I'm going to try to give you all of them. All of them. If you're here taking good notes, putting stars by things, the short answer question should be the easiest ones. Okay, so we know a little bit more about the plasma membrane. Everybody good with this? Practice drawing that a few times. Make sure you can explain it to somebody who's not taking anatomy. Then you should be in good shape. Let's take a look at the official picture from the big green book. If you squint, you can see that there's some circular heads with 2 tails. You can see some gigantic proteins, and you can see that some of the proteins are on the outside, on the inside, yeah. So we're good, right? When we think of the ingredients, I'm not going to ask you percentages or numbers. No one needs to study percentages or numbers. But you can see that the plasma membrane is mainly lipids. Most of those lipids are phospholipids. And you can draw one. Circular head, 2 tails. Yay. We said that there are hydrophilic heads and hydrophobic tails. So far, so good. We've just drawn this. This is all review. But in addition to phospholipids, write down this, that there's, or circle this on your lecture outline, that there's another fat called cholesterol, which is something that a lot of people are really concerned about, or taking medications to lower. Some people think cholesterol is like the worst thing ever. But like we talked about on Thursday of last week, we said cholesterol is a necessary component in terms of making things like steroids, estrogens, and testosterone. But in the plasma membrane, it's important to make sure that the phospholipids stick together. It's important, right? So it's not too leaky. So when we think of cholesterol, think of it as a major ingredient in holding the phospholipids together. There's even a third type of fat called glycolipids, and this is the lipid that's on the very outside of the cell membrane, and sometimes it makes it sticky, so things may want to attach to it. That's kind of nice, especially if we're interested in communicating. Okay, so those are the facts. I would say know all 3 and a little bit about those 3. That would be a good short answer, multiple choice question. So here's a picture of the phospholipids yet again, circular heads. We have hydrophobic tails, and then this yellow stuff they're trying to kind of call cholesterol. Do you remember the term that we talked about on Thursday when something has both hydrophobic and hydrophilic? We said that they were what? Amphiphilic. Yeah, so you can write that down in your notes, right? That a plasma membrane is amphiphilic. Okay. Let's talk about the proteins, the second major ingredient. So we have membrane proteins, and even though it only makes up the remaining 2% of the ingredients, it's a pretty big 2%. 50% of its weight are these gigantic proteins. Of course, you do not have to study the number 50% or 2%. I'm never going to ask you those. I'm not into numbers unless I tell you. When you look at these proteins, we describe them as being peripheral, integral, or transmembrane, like you see here, proteins. So one of the kind of the things we're going to look at today is what's able to pass through cells, transport, and lab. So we'll be talking about pore size. And then we said peripheral proteins have a lot of functions and they attach to the outside of the membrane surface. So they have lots and lots of functions. So many that when we talk about their jobs, we can only say that today we're going to introduce them, but throughout the entire year, both this session and next session, you're going to hear a lot more about these proteins. I think that this one's worthy of a picture, so I'll give you a second to whip out your camera. Take a picture of this. This tells you 1, 2, 3, 4, 5, 6. There's even one more on the next slide. These are 6 functions of the peripheral proteins. I think you should know a little bit about each one of these 6 different functions. Because I'm not making you memorize it because I'm telling you that you're going to hear more about these in both semesters. This is really, really important. So let's start with this first example of a protein that kind of sticks all the way through to the outside, and we call it a receptor. Well, we've already talked a little bit about receptors, but we called them substrates. And we said that they have active sites. So one of the things you can see here is that a receptor has an active site for something very, very specific. So when we talk about things attaching to the plasma membrane, not all things, not everything, but just something specific can attach to that receptor. So different cells have different receptors. We talked about this on Thursday, how proteins can act as enzymes, which we call catalysts, speed up reactions. So there are enzymes on the membrane of cells. That should be good. Remember, all enzymes are proteins. That three-dimensional blob that looked like a popcorn kernel, same idea. We spent some time talking about the fact that proteins can act as channels or pores. But the next 2 examples of these channels, or this one I should say, is something really specific. And I want you to underline this. The fact that some channels are gated, and underline that word gated. We're going to be talking about gated channels for our 3rd test. When we talk about how muscles contract and how they relax, we're going to be talking about gated channels. So let's make this really easy. A channel is a pore. A channel is a pore. When we look at this, it says that some molecules can make it in or make it out based on the size. If something's bigger than this pore, it's not going to get through. Sometimes the pore says you can get through if you are a certain charge. If you're positively charged, you get through. But a gated channel, this is like living in one of those rich neighborhoods or going on vacation and staying in a really nice place. And it's a gated community. You pull up and you have to give some password or code or you have a card. It says, I'm going to stay closed unless you show me the right credentials. So we have 2 types of gated channels that I want you to write down. One type of gated channel is called a voltage gated channel. Write that down. Voltage, like electrical. It says that it only opens if it gets zapped by electricity. Do you believe that? So when we talk about brain signals, they're electrical. So when your brain sends a signal to certain parts of your body, it stimulates, look, voltage-gated channels to open. It's sweet. The other type of channel is called a ligand-gated channel. So a ligand is an official name for some type of chemical that has to bind to the gated channel and then it opens. Only if it binds to it. So these channels are neat because they stay closed 99% of the time unless something triggers them. Whether it's some chemical, a ligand, or some type of burst of electrical energy, like a brain signal. Down here is something that we won't talk about, but it's kind of fun to talk, we won't talk about until next semester, which I don't think I'll have you, but next semester, when you talk about the immune system, you're gonna say, wait a minute, how does the immune system know that this cell is a part of you? Because every cell in our body has cell identity markers. That's sweet. And if you have a cell inside of you that it's never seen before, like a bacteria or a virus, then your immune system's gonna say, whoa, I recognize on your plasma membrane, you have a cell identity protein that I've never seen before. You're bad, you're foreign, I'm gonna destroy you. That's the way it works. That's the immune system. Unfortunately, right, sometimes as we get older, or sometimes we develop diseases, it says to our immune system that we can't distinguish what belongs to us versus something foreign, and we have autoimmune diseases, like Crohn's, like rheumatoid arthritis. Those are big ones. Oh my gosh, there's many more. That means that there's some flaw with your immune system and these cell identity proteins. Okay, lastly, on this slide, you can see something that says that cells need to stick together, sometimes literally, to combine and form maybe a barrier. And we have proteins that allow them to stick together. So, all of this talk is dealing with proteins in the plasma membrane. Each one of these probably has 1 or 2 full lectures dealing with it. So today, we spent 10 minutes kind of introducing it. So hopefully you can kind of remember this and explain these on the exam. Okay. The last type of, and don't take a picture of this, the last type of protein interaction we have in the membrane is something called the second messenger system. So write down second messenger. And next to second messenger, I want you to write down the fact that the purpose of second messenger proteins is to make more enzymes. If you remember that phrase, you'll be good. What does the second messenger system do? It makes more enzymes. End of the story. Do you have to study all these steps and know all these crazy enzymes? Nope. You don't know any of this. But if I ask you on the test, what's the purpose of the second messenger? What's the purpose of cell identity? What's the purpose of a voltage-gated channel? You should be able to tell me just the general purpose. The purpose of the second messenger is to make more enzymes. We'll get into more detail later. Okay, so here you can see a table from the big green book that talks about each one of these functions and puts it in a table. So if you're into the green book, you can look at this module and find this table. Sometimes people will say tables are helpful. In addition to the plasma membrane being a protector, occasionally it has some weird things like these projections called microvilli. Now remember, microvilli are on some, but definitely not all cells. Microvilli are found in places like our intestines, where we have absorption of things that we ate. So just some cells have these. Some cells have these little hairs. Notice they're not finger-like projections, they're hair-like projections. So when we think of these hairs, their job is to create a current. So in males and females, we have these hairs inside of our respiratory tract. And for us who don't have cystic fibrosis, every time we go like this, clear our throat or cough, we say, thank you, little hairs, cilia, for moving all that crap up so we can cough it up or clear our throat. But people who have cystic fibrosis, listen to this, they don't have those hairs. They have to strap on these chest contraptions, and they vibrate their chest like this, really fast, trying to break up the crud that's in their breathing tract. It's tough. Or when you think of cilia, I want you to think of female reproductive structures. This is pretty sweet. When females ovulate once a month, how does the egg get from the ovary down to the uterus? It rides a current of cilia. It's pretty sweet. So whenever you think of hairs, just think it's generating some type of current. That'd be good enough for me. Oh, this is the dreaded slide for some of you in lab. You never want to see or talk about sperm ever again. But this is the only example of a cell that has a big long whip called a flagella. That's the only thing you need to remember. So females have no cells in their body that have a flagella. Okay, so now we get to move into a topic that usually causes a lot of sweating, stress. So that means we're going to do a lot of drawing. So I'm going to erase all this. We're going to talk about the plasma membrane and transport. This is going to be a part of tonight's lab. So this is a big one. There will probably be 2 questions on the lab test dealing with what we're going to draw, and probably 5 questions on the first test dealing with just what we're going to draw here. So stay focused. We need to be able to focus here. We're going to talk about transport across. So here we go. There's 2 types. There's passive transport and there's active transport. When we say passive transport, we're saying movement across the plasma membrane that requires energy. It requires no energy, without energy. Passive means no energy required. Active requires energy. And whenever I say energy, I'm going to be talking about a molecule called ATP. Think of it like the electrical substance that drives a machine. The machine won't work if you don't plug it in. Passive says that there's literally means it's unplugged, no electric required. Active says you need help, you need energy. So we're going to talk about passive first, and there's 3 types of passive movement. There's diffusion, osmosis, and filtration. Sometimes I will sit down at the old dinner table, my wife will say, well, what did you teach about today? She asks me that probably twice a year. She doesn't want to know what I teach about. And I'll say, oh, I taught about osmosis. And she'll look at me like, oh my gosh, that's horrible. How do they stay awake? You know? So when we think of passive movements, it is really boring, but it's really, really important. So we're going to talk about each one of these. What you need to do for the exam, ready, is you need, here we go, to be able to talk about an example of each and answer the question, what is the driving force that causes this movement? So let's start with diffusion first. Diffusion is a passive movement, no ATP required. Diffusion is the movement of anything from an area of high concentration to an area of low concentration. Diffusion is the movement of anything from an area of high concentration to an area of low concentration. Okay, so let me give you an example. When my youngest son, Josh, was in preschool, all my friends called him the Axe Man. because he had every flavor of Axe body spray. This is preschool. So he would get in the car and I'd say, yo, Josh, you're smelling good, brother. But you need to go a little light on that Axe body spray. And he was just going, you know. So when Josh would get to preschool, the people sitting next to him would say, whoa, Josh. And then by the end of the morning session, everybody could smell Josh. So we all have some examples of that, right? Where we're sitting next to somebody that smells really good or smells really bad. And eventually people smell that because we have concentrated moving to lower concentrated areas. Or think about this, this is a better one. When my wife or my daughter makes chocolate chip cookies, oh man, I could go for about 3 of them right now. And my wife opens up that oven door, it's bursting with chocolate chip cookie molecules and it's going through our entire house. So eventually people are like flocking to the kitchen saying, where's the milk, right? Because it's moving from an area of high concentration to an area of low concentration. That is diffusion. We're going to see some examples today in lab. Remember, anything that's moving from high to low is diffusion. Done. So we can say, don't say chocolate chip cookies, but you can say molecules, whatever. There's lots of examples. And the driving force, here we go, is just simply a change in concentration. High to low. Osmosis. Simple definition, it's the diffusion of water. Oh. Which means that it's the movement of not anything, that's diffusion, it's the diffusion of water. Osmosis is the movement of water from an area of high concentration to an area of low concentration. And the driving force is the same. So today in lab, we're going to do an experiment, Thursday as well. And I want us to kind of draw a little bit about what we might see. So let's take a beaker and let's put some fluid in it. And guess what we're going to put into this beaker? We're going to put in red blood cells. But not human red blood cells, we're going to put sheep blood. Yep, we're really going to do it. So sheep blood, we're going to surround it with different solutions. So when I give you a question on the test about what happens when cells are placed in other solutions, we have 3 questions to ask. If some of you try to do what you did with the microscopes and jump from scanning to high and not follow the steps, you're going to get lost. You'll get all the questions wrong. But if you follow these 3 steps in order, you'll get every question right on the lab test and on the lecture test and on the NCLEX test. This is what I'm going to go over right here is usually something that I'd say 40% of the class will miss on the exams because they just jump to like conclusions. They say, there's no thinking, I'm just going to memorize or guess. So you don't do that, just follow the steps. So what do? We say, let's first talk about the red blood cell. And we're going to compare it, ready, to the solution outside of the cell. So let's say we're going to put the red blood cell into Walmart premium distilled water. Okay. So right now we have 2 solutions. That's how you attack these questions on the exam. They could be lengthy word problems or whatever. All you have to do is say, okay, what are the 2 solutions that I'm getting? Draw it. I will always give you the concentrations of the solutions. So here's how it works. In distilled water, we're going to say that there's 0% stuff or solutes, and it's 100% water. So let's review back from 2 lectures ago. Remember, we said a solvent plus a solute equals a solution. So we said blue stuff plus, oh shoot. We said water plus blue stuff equals blue Kool-Aid. So the solvent, the universal solvent is always water. The solute stuff, whatever that is, in this case it's blue. And then the final product is Kool-Aid. So the two solutions that we're dealing with is distilled water, which is kind of really not a solution, it's just a solvent. But a red blood cell, ooh, here we go. We're gonna say that a red blood cell has 0.9% solute. I'm putting 4 stars by that because that is a percentage that you should remember for the rest of your life if you're going into the medical field. This is like the number, this is like the equation, what is 2 times 2? None of you have to think about it, you just are like a robot, 4. If I say, what is physiological saline solution? What is the concentration of any cell in your body, you're gonna say it's 0.9%. Because as a future nurse, you're gonna be giving people saline. As someone who uses contacts, you squirt saline solution in your eyes. That is 0.9% solute. It's a fact that you need to know forever, including this first test. So don't forget that. Forget that. So that means it's 99.1% water. So now we have all of the ingredients of the 2 solutions. We just need to ask and answer 3 questions. You do this on the test, you win. Okay, question number 1 is, which solution has most solutes? How easy is this? So 0 versus close to 0, but more, 0.9. So this is the solution that has the most solutes. We call the solution that has the most solutes, right? Hypertonic. Remember the prefix, hyper means excess amounts of, more. Please just ask these 3 questions and you'll get the question right. No thinking involved. It's just really just kind of follow the recipe. Second question. Which direction will water move? Well, in order to answer that question, we have to say, what is the definition of osmosis? It's the diffusion of water. Water moving from an area of high concentration to an area of low concentration. So, we just look at the concentrations of water, everybody ready? 100% outside, can't get any more than that. Close to it, 99.1, but slightly less. So that means water will go from 100 to 99. Water will move, look, into the cell. So in this case, we're going to write the words into the cell. Third and final question. What happens to the cell? So there's some lingo that we have to use. I mean, somebody tell me, Taylor, what's going to happen to this red blood cell? You know, I drew it, right? What's going to happen to it eventually? Taylor, go. Come on, Taylor. The arrows are saying water's going into it. What's going to happen to it? I can't hear Taylor. What, go?
It's gonna swell up.
Yeah, right. So it's going to swell, and eventually it's going to burst. So we're gonna say that eventually, there's going to be lysis. Yay. You just answered one of the questions on the exam, 1,000,000%. We're gonna be doing this exact little study today in lab on Thursday. Let's take a beaker, put some water in it, and put a red blood cell. And let's put the red blood cell in a solution of 10% salt. I'll let you fill out the rest. Go ahead and do that real quick. So tell me the percentage of water, and then write down the percentages of solutes and water for the red blood cell. Mary, tell me the answers. Go. How much water?
There we are, 90% water.
90% water, okay.
So,
And then red blood cells what? You have to memorize this, Mary. Give me one.
0.9,
Okay, and,
then 99.1.
yay, Mary. Okay, so that's step one. Okay, step two. Let's go to my man Vince. Vince, answer question number one. Which solution has the most solutes, the red blood cell or the solution outside?
On the red blood cell.
Vince, do you want to do jumping jacks? See, Vince just like was a robot. Come on, Vince! 10%, brother, versus 0.9. So we're gonna say this one is hyper. Since you got it wrong, Vince, I'm coming back to you. This, by the way, you could say is the solution that has the least amount of solutes. You can call that the hypotonic. You may have heard of that before. Vince, question number 3. What happens to the water? Water will move into or out of, and tell me why you're saying it. Go.
It will go out of the cell.
Because why?
Uh,
Because why? Quick.
this-
Because why?
because high to low.
What's the definition of osmosis?
High to low.
High to low. So what's the percentage of water outside? 90. What's the percentage inside?
99.
Yeah, so it's gonna go from 99 to 90, right? High to low. So water will leave the cell. Taj, what happens to the cell over time? It shrinks, good. Or some people will say dehydrate, or some people will say shrivel. But on the test, you're gonna use the lingo. You're gonna say it undergoes, look at this, crenation.
So it's either lysis or crenation.
Yep, unless we put a red blood cell, look at this, in saline solution, which is, look at this, 0.9 and 99.1. So during surgery, do they rinse out wounds with distilled water? No, that would irritate the tissues. Think about this. Sometimes after having surgery, like oral surgery, listen, they say rinse out with salt water. I wonder why. But in case of this situation, we have a red blood cell placed in a solution that is identical. 0.9 and 99.1. So let's answer the first question. Josh, which solution has the most solutes?
They have the same.
They have the same. So there's neither hyper or hypo. You say that it's an isotonic solution. Okay, Alexis, my friend Alexis. In which direction will water move? Alexis? Because the definition says water will move from high to low. What's the concentration of water outside of the cell? Quick. David. Okay, so that's a good guess. She said they would stay the same. What I want you to do is I want you to draw this arrow saying that water moves freely in both directions. This is exactly what happens in our cells right now, is that they're surrounded with an isotonic solution. Okay,
Because it's not gated though,
right.
right?
In fact, there's even special pores for water. Okay, so we've talked about diffusion, we've talked about osmosis, and then the last one that we have to talk about is an example of filtration. So the best example of filtration that I know of in the human body would be our kidneys. They're filtering blood like crazy. And what drives filtration, ready? The driving force? It's not a change in concentration like we have for osmosis and diffusion. For filtration, the driving force is a change in pressure. So, when we think of the driving force, I want you to think now why people with high blood pressure can have kidney disease. That makes sense to me. If you have too much blood flowing through your kidneys can like explode. If you have too low blood pressure, that means your kidneys may not filter enough. That's bad too. So your kidneys, listen to this, maybe this you didn't know this, help regulate blood pressure. Your kidneys help regulate your heart. What? You'll learn all about that second semester. Okay, yay. So I hope you're going to say now, hey, transport, not as boring. I think I can get it. But if you still feel like, oh my gosh, hypertonic, oh, then we're going to do it in lab tonight. We're going to do it in lab on Thursday. Okay, so let's go through these slides quickly. Okay, you're responsible for them, but I think we've talked about them on the board, so we can just fly through these and just highlight. It's all review. So we said passive says no energy. Active requires energy. So far, so good. Filtration, we said, is driven by pressure. Best example would be blood flowing through our kidneys. And in this case, it shows blood flowing through very tiny vessels called capillaries. Notice the very tiny pores. The only way that things get out through the capillaries is through blood pressure. We said diffusion is the movement of anything from an area of high concentration to a low concentration. Sometimes we say that when things move from high to low, it's moving down a concentration gradient. It just means from high to low. So we're going to do an experiment in lab. Actually, I set it up already before lab. You'll thank me in lab. Where I put some dye molecules in the middle of a plate, and we're going to measure how much those dye molecules, ready? Not move, how much they diffuse. So when we look at the rates of diffusion, you have to say, what are some factors that affect how things move from an area of high to low concentration? Put stars by these. Every one of these will be on the test. So that means, first of all, you have to say that temperature can affect how fast things move. Generally, if we warm something up, it's going to cause something to diffuse faster. The molecular weight, what the heck? That means the size of a molecule. And next to this in your notes right now, right in your outline, write the word lab. That's what we're doing in lab tonight. We're checking the molecular weight of certain molecules and how fast they move. The rule is, large molecules, just like people, in most cases, large molecules move slower than small molecules. I always say, here's the example. If you had a race between like an offensive lineman on the Bengals, some 6'10", 500-pound guy, and say, let's have a race against some running back. Who's gonna win? The smaller dude, right? Small molecules move fast, large molecular weight moves slow. That helps you know. This says the difference between the concentration of both solutions also influences it. So if you have two solutions or two areas that are very similar, the movement is going to be slow. But if it's a huge difference, then it's going to move fast. Try to equal it out. Membrane surface area, that's a big one. How wide the membrane is. And how big are the pores, the channels. That has an influence on how fast things move through the membrane. So I think you should know those. I think probably that would be a great multiple choice question. Like, which of the following does not affect the rate of diffusion? I'll have all of these except one crazy one, right? So osmosis, we said it's the movement of water. In this example up here, you can see a beaker that has a solution, two solutions, solution A and solution B. On side A, it has a bunch of red dots, which means these are the solutes. So here we go. Let's answer the questions. Ready? If I said which solution, side A or side B, is hypertonic, everybody in harmony, side A has the most stuff. Side B is the hypotonic solution. So which solution has the most water? It would be side B, right? Water always moves from high to low. So over time, look what happens. The water moves in and the water level rises. That makes sense. Okay, yay. So far so good. If I said hypo, hyper, and iso, you guys are good. There's no memorizing any definitions for the test. I will not give you any definitions of hypertonic. So if I were you, I would write some examples down. Let's do that. So for hypotonic, I would write distilled water. If you come to me during office hours and you say, Mike, I don't understand the differences still, I'm gonna say to you, give me an example of a hypotonic solution. You better say distilled water, nothing in it. Hypo means low solutes, low amount of stuff. There's no better example of a hypotonic solution than distilled water. Hypertonic, I would write down McDonald's sweet tea. About 3 years ago, that used to be my go-to, especially in the summer. I would actually stop at McDonald's and go in so I could drink and then refill on the way out. But I can't do that anymore. Because last year in the summer class, I had someone who worked at McDonald's and they told me how many solutes were really in that hypertonic solution, how much sugar. It would take literally probably an hour on the treadmill to cancel out one sweet tea. I just can't do it, right? Not at my age. I'd be obese. So, sweet tea, the glory days of old. Isotonic. Soda, as long as it's diet. Isotonic, here we go. Isotonic is physiological saline solution. Saline solution, stuff that you squirt in your eyes. Okay, now you got it. So take a look at this. Oh, let's go back one. Let's take a look at this. Instead of a red blood cell in a beaker, what if I gave you a fish in a bowl and said, what if we took this goldfish from the carnival that we won and put it in ocean water? Oh, that's not good. you not only will tell me that the fish will die, but I would need to know details. Like, how did the fish's cells die? So you'd have to say, okay, I put the fish into a hypertonic solution. Instead of guessing, which some of you are doing right now, that's how you get all the questions wrong on the exam. You say, I'm gonna write over here, fish's cells and seawater. And I'm gonna write down the concentration of solutes in water, ask the 3 questions, and you're gonna get it right. But I'm gonna say 50% of you will get the question wrong on the exam. 50, because you're gonna jump. You're gonna start saying, I know that, I'm gonna guess. I memorized this, I'm a robot. No, you gotta write it down and avoid making a simple mistake. In lab, we're gonna deal with red blood cells, and we drew this, so this should be complete review. It says, look, in an isotonic situation, we have, look at the arrows going in both directions, which means the concentration of solutes is exactly the same, the concentration of water is exactly the same. But if you put a red blood cell in a beaker of distilled water, oh my gosh, water's gonna rush in, it's gonna cause lysis. If you put red blood cells in something like 10% salt, oh, it's gonna crenate, shrivel up. So our job in lab today, ready? On Thursday, and on the lab exam, is for you to have pictures on your phone of this, this, and this. Not this picture from up here, but literally what it looks like. Can you recognize red blood cells when they're tortured? They're blowing up, or they're crinkling up, or they're happy. That's one station on the lab practical. And it should be good, because you're gonna have pictures on your phone today. Okay, sometimes, let's talk a little bit more about passive, and then we're gonna wrap things up. When we talk about passive transport, sometimes the molecule that is getting transported across the membrane needs a little help. So sometimes there's proteins that bind to that molecule, and we call it carrier transport. These are sometimes, look, diffusion, and sometimes they're active. So whenever we say carrier, it can go either way. If I say facilitated diffusion, means there's a protein that facilitates or helps diffusion. That is always passive. So let me give you an example. Here is a protein that says that if I bind to, if I bind to a molecule and transport it, I can carry it across as long as I don't reach what I call my membrane saturation. So remember what we drew on the board on Thursday. We said that proteins look like a wad of gum, and we said the active site looks something like this. Now we can add this business, right? And say sometimes these proteins are wedged in the phospholipid bilayer. And it says that there's only a limit on how many molecules it can bind to. If we have way more molecules, substrates, then it's not going to have any effect. So it can reach saturation. So what this slide simply says is that proteins have a limit to how many things that they can transport. Sometimes proteins transport in one direction. Look at that, one solute at a time. Sometimes proteins can carry 2 or more solutes in the same direction. Sometimes this protein can carry them in opposite directions. Look at that. Uni, sim, and anti, make sure you know those 3 prefixes. Those are all membrane protein carriers. And like I said, when you see the word facilitated diffusion, remember that there's no ATP, so this is 100% passive. It just means that you have a protein that helps it cross. So the last thing we're going to talk about today is the active transport mechanisms. And all I want you to write down in your notes is the word pump next to active transport. It's something that requires energy. Active transport is something that would not happen without ATP. So here you can see one of the best examples of a pump in human biology. It's called the sodium-potassium pump. You don't need to study anything about the sodium-potassium pump. You don't need to know any of these letters or anything. But you need to remember this for the test, that if you see the word pump, you're going to tell me it's active. And when you say active, you're telling me it requires ATP. That's it. So here it says that in order to get potassium or K or sodium, Na, in and out, it requires ATP. This will not happen by diffusion. Okay, it's as easy as it gets. That's all I'm going to ask you. Some examples of active transport other than pumps are the ways that cells drink and the way that cells eat. Combined, we call this process, and underline this in your outline, phagocytosis. What a name. Phagocytosis. It's the process of eating, digesting, and spitting something out. Wait a minute. I think I found a spot in the room where I feel cool air. You guys feel it? You feel it, don't you? Yeah, I stand by you. I feel cool air. Eating, digesting, and spitting out is the process of phagocytosis. So if we break those down, ready? The eating part is called endocytosis. I mean, that makes sense, right? Endo, in. Spitting out is exocytosis. You can see an example of this. Don't take a picture of this. But this is the way our immune system works. It says, look, there's a bad guy. This thing could make us sick. So what I'm going to do is I'm going to eat it, endocytosis. I'm going to digest it, and then I'm going to spit it out, exocytosis. All of this happens only if we have ATP. Okay. All right, cell eating, phagocytosis, don't forget. Okay, I'm going to skip the next 3 slides, goes over detail that's way too intense. Just as long as you know endo and exo. The last slide of the day deals with the second component of the cell. And this is the cytoplasm. And here's what I want you to write down. In lab, we're going to learn some organelles in tonight's lab. Organelles. On the lecture test, I'm going to say you only have to know the organelles that we cover in lab. So that's a theme now, right? I'm only testing you on the anatomical terminology that you learned in lab. I'm only going to test you on the organelles that we learned in lab. If it wasn't in lab, it won't be on the lecture test. This is a way that you can study one thing and get credit for 2 classes or 2 tests. So that should be kind of nice. Okay? So when you see the word cytoplasm, I want you to write down the word organelles, which literally means tiny organs. So instead of saying we have a spleen and a stomach inside of us, we have things like the mitochondria and the ribosomes and things like that. So what I would do, and I'm going to talk about this tonight and Thursday night in lab, is that I would make the organelles flashcards. I would put the name of the organelle on one side and then what it does on the other side and call it a day. And it'll be good for lab and lecture. All right, so this was a typical lecture. It's cranking up a little bit, right? So we'll see you guys on Thursday unless you have lab night. If you have lab, we'll start at 7 o'clock.